Swayam Prabha. Digital India. Educated India.
So hello everyone. So today is the first lecture for the course Geotechnical Earthquake Engineering. So this course I am offering for UG as well as PG students. So this is offering as an elective subject. So, but before you take this course, you should have some knowledge of soil mechanics and foundation engineering, or sometimes we call it Geotechnical Engineering 1 and Geotechnical Engineering 2, because I will frequently use a few terminologies. Those are very common in soil mechanics and foundation engineering course. So, if you do those courses, or if you take those courses, then it will be easier for you to understand those terminology, because I will try to explain most of the terminologies or the terms that I will use during my course, but few things, those are very common, I will not discuss, because then it will take some more time and it will actually reduce the content of the original course. So this is one thing, and another one, the practicing engineers, those are working on this area, and those are want to design the geotechnical structure under earthquake loading, so they can also take this course. So let's start this course. So first we should know what is earthquake. Okay, so earthquake is the striking or shaking of earth subject due to sudden release of accumulated energy in the earth lithosphere. Lithosphere is right now, I will explain what is lithosphere later on, but right now you just assume that this is the uppermost surface of the earth. It has some other layers also that I will discuss. So that means somehow the energy will be accumulated and then that will release. Okay, and when it will release, then there will be a shaking of earth surface will occur, and then sudden release of energy will create seismic waves, or in other way we can say that these energies are released in the form of seismic waves, or it creates the seismic waves. Now when we are talking about that earthquake engineering, so that means this definition of earthquake engineering means it deals with the effect of earthquake and the method to reduce those effects, because we are talking about that there will be a shaking on earth surface. So because of the shaking, so it will create effect on human life and the structures those are built on the earth or earth surface. So that means the earthquake engineering will deal the effects of this earthquake and how to reduce those earth effects. Okay, so that means our idea is not to stop earthquake, because we cannot. Okay, so but our idea is that so that we can reduce the damage or reduce the effect as much as possible. So that is the idea, and those things will be discussed in this course. Now when you are talking about this deals the effects of earthquake, then it has different aspects. Okay, so it has structural engineering aspect, it has geotechnical engineering aspect, geological aspect, seismological aspect, then risk analysis. So these different aspects are there. So in this course of geotechnical earthquake engineering, we will only discuss the geotechnical aspect of earthquake. Okay, so that means how to take care of the geotechnical parameters, how to design the quake ground motion, then that will be useful for structural design, and then what are the other geotechnical properties that you have to determine for the design of geotechnical structures, and then some other geotechnical phenomena that also will be also discussed. So that means we will concentrate only the geotechnical aspect in this course of geotechnical earthquake engineering. Okay. So now before we start the original content of this course, then we should know what are the different important seismic hazard. Okay. So as I mentioned that there will be some effect of earthquake. So what are those hazard? Okay. First hazard is the ground shaking, because as I mentioned that in my definition that is the shaking of earth's surface due to release of accumulated energy. So when the energy will release, then there will be a shaking on ground surface. Now this is the most important seismic hazard among the all seismic hazards. Okay, the strength and duration of this shaking that depend on the size and location of earthquake and on the characteristics of that site. So that means what is the size of the earthquake, whether it is a large earthquake or moderate earthquake or shallow or small earthquake, which type of earthquake it is, it depends on that. It depends on that your site or the location of interest, how far from the locus or the focus, I should say, focus of the origin of the earthquake. Okay, and that your characteristics of the site. That means the site where you are interested, what is the characteristics of the site, then what is the soil or rock characteristics of the site. So those are very important to know. Now next one is that as the uppermost part of the earth is soil, and now when this energy is released in the form of wave, so this wave will definitely travel to this soil, and we know that soil properties change very significantly if you change the location. Okay, that means very within a small distance the soil properties will change or soil property change. So that's why these characteristics of the shaking will also change as the property of the soil will change. So that's why ground shaking may vary significantly within a small area because of the change in the characteristics of the site. Now next hazard is the structural hazard. Now the structural hazard means when there will be shaking, so we have to design our building in such a way that there should be earthquake resistant. Design of the structure that should be considered. Okay, and to need the accurate prediction of ground motion, that is also required to design of this earthquake resistant structure. So that means we have to do the earthquake resistance design of the structure, and to do that we have to accurately predict the ground motions. Okay. So next one is the another important phenomena, that is your liquefaction. So that means the strength of the soil is reduced significantly because of this effect. Okay. So later on all these things will be discussed in detail, but this first lecture I am giving the different types of hazard, and then there how to prevent them, those things will be discussed in the later stage of this course. So that means, so now you know that liquefaction is a loss of strength of the soil, and in such that the strength is reduced in such a way that soil is unable to support on the structure and become unstable. Because when the strength of the soil is reduced, then if you place the structure on it, or a structure is always originally on that surface and it reduces its strength, so definitely it will be unable to support the structure and it will become unstable. Okay. So next hazard is the landslide. So this landslide means earthquake induced landslide cause damage of buildings and other construction facility. An earthquake induced landslide can occur due to liquefaction. Okay. An earthquake induced landslide can occur due to the failure of marginally stable slope under static condition. That means slope, those are marginally stable during static condition, will fail or may fail during the earthquake loading, or that means we will consider the extra load that is coming for the earthquake, and it is marginally stable in the under static condition, so it will fail if earthquake comes. So now next hazard is the retaining structure failure. So that means the retaining structure, especially waterfront retaining structure, are damaged due to earthquake. Okay, so that means we have to design this structure considering the earthquake force also. So those will be discussed later on. Next one is the lifeline hazard. So what is the lifeline? Lifeline means all the facilities that we use. That means the transportation facilities, and roadway, railways, then the electricity, then the water pipes or sewerage line, then your oil pipes or the oil storage facility, or your oil refining, or then your transportation tower. So all these related facility will be damaged due to earthquake, so that there will be a total damage of the system, and your life or human life will be affected due to this earthquake. Now the last hazard, that is the tsunami hazard. Now what is tsunami? That when the earthquake occur, okay, and then if it is the your below sea is the source, then what will happen? The wave will generate, and that will create a tsunami. How that means? That in the, you can see in the picture that in the sea, if it is the open sea, the tsunami travel great distance with high speed. So if you can see that this figure, that you can see that in this figure, this speed is around 800 km per hour in the open sea, and when it reaches to the shoreline, then the speed is around 50 km per hour. So that means in the open sea, the tsunami wave travels great distance with high speed. But in open sea, the height of the tsunami wave is less than 1 meter, and wavelength, that means distance between the crest, of several hundred kilometers. So what is wavelength? Now if you can see there is a tsunami wave, then this distance is called the wavelength. Okay, so delta, this is your wavelength. So in the open sea, the wavelength may be in several kilometers, but height, you can see that height is only 1 meter or less than that. But when it reaches to the your shore, then the speed of this tsunami is reduced, but height increases. You can see that height will be increased. So that's why the height is the major issue in case of tsunami, because that will create the maximum amount of damage. So these things, these are your seismic hazards. Now how I will protect the ourselves from these hazards? So there are few steps that I have mentioned. These are not only these steps, there are other steps also, but I have mentioned few of them. So that means first we have to produce seismic risk map. That means we should know, we have to produce the soil and rock type map. We should have the liquefaction potential map and the landslide potential map. So that means we know that for a particular region, what are the soil types and the rock type. And then we should know the local liquefaction potential. That means in the site whether liquefaction will occur or not. So which side liquefaction possibility is there, which side not. So we should have that. We should have that type of map. Then landslide potential map also. That means whether this site, the landslide will occur or not. So we should have this information. Okay. So before we do some construction, so that we can take care during our constructions. Now the identification of active or hidden faults. Now the waterfalls are the localized area of weakness in the surface or the crust of the earth. So that means later on I will discuss in detail what is fault. Now the definition means it is basically the weak portion in the surface or the crust. Now during when the energy is accumulated, now these energies are released within this weak portion. So that means the fracture may occur along the fault line and then or the fault zone, and then energy release. Okay, so that means we should identify these faults. That means if these faults are active faults or even hidden faults. Sometimes we have the hidden faults, so those also we have to identify. Then the earthquake resistance design of the structure. As I mentioned, that one step is definitely we have to design the structures such that it should be earthquake resistant. Okay, so that means earthquake resistance design of such structures should be done. Then proper selection of the site for the critical facilities. That means if you want to construct some critical facilities like dam or your nuclear power plant, that means we should place those facility as far as away from these faults. Okay, so that's why the information of faults is required, okay, and important. So and next one, if we have the tsunami, then the tsunami warning system if we can develop. So this way we can minimize these damages and we can take the protection against this seismic hazard. Now when we are talking about the earthquake, there are another two terms, those are important or those are required to know, is that foreshock and aftershock. Foreshock are the small earthquakes often occur before a major earthquake. Okay, and aftershock, a small earthquake often occur after a major earthquake due to the result of adjustment, because during the adjustment this earth interior is damaged or changed. So because of that some adjustment will occur. So because of this adjustment some small earthquake will also occur. Sometimes this aftershock also we have to analyze. So that is also required to know. Okay, so now next one is that, so that means I have planned in this course in such a way that I can take care all these seismic hazard. Okay, so that's why in the first part of the course I will discuss about the cause of earthquake, then continental drift and plate tectonics theories, then plate boundaries, then faults, seismic waves, that is also important thing, and the location of an earthquake epicenter, how to locate an earthquake epicenter, the size of earthquake, as I mentioned, this earthquake is a small earthquake or there's a large earthquake or moderate earthquake, the size of an earthquake, then that means it has the magnitude and intensity based scale, so those I will discuss, and the energy of earthquake, how much energy is released due to an earthquake. Then I will discuss about the strong motion measurement, then ground motion parameters, because as I mentioned that if we want to design or if our structure, during the design of structure we should do the earthquake resistance design of the structure. So to do that we should also properly predict the ground motion parameters. So that's why that is also required. So ground motion parameter, estimation of ground motion parameters will be discussed. Then measurement of dynamic soil properties, those will be very required later on when I will discuss about the design of different geotechnical structures. So that I will discuss as well as field test and the laboratory test. And then I will discuss about the model test also, what are the different types of models test. Then the stress strain behavior of cyclically loaded soil, we will discuss about equivalent linear model and the non-linear model. And then I will discuss about the 1D ground motion response analysis, okay, because sometimes the parameter that we will get is mostly for the bedrock, okay. So that means, and then we require to know what are the parameters at the ground surface. So from the bedrock to ground surface, how we can from the bedrock motion, known bedrock motion to a ground surface motion, how we can predict that. So that also we will be discussed, and vice versa also. If we know the ground motion parameter for ground surface, Then from the bedrock also you can get from the bedrock to ground surface and ground surface to the bedrock if we have a soil layer above the bedrock. Okay, so that means there are different approaches, the linear approach, equivalent linear approach and non-linear approach, those will be discussed. Then the liquefaction, what are the different types of liquefaction? Flow liquefaction, cyclic liquefaction, definition of liquefaction. Then how to evaluate the initiation of liquefaction. That means a particular site whether liquefaction will occur or not. How we will know that? What are the different approaches? Laboratory approaches, field approaches. Okay, those will be discussed. Then cyclic, there are different approaches, cyclic stress approach, cyclic strain approach, those will also be discussed. Then liquefaction susceptibility criteria for silt and clay. Okay, what are the liquefaction susceptibility criteria for silt and clay or fine grained soil? Those will be discussed. And evaluation of cyclic softening in silt and clay, that will also be discussed. Then earthquake induced settlement of soil will be discussed. Next stage, I will discuss about the soil improvement technique to mitigate the liquefaction hazard as well as the earthquake hazard. Okay, mainly I will discuss the liquefaction hazard, but at the same time, if you use those ground improvement techniques, earthquake hazard will also be mitigated. Okay, so that means the liquefaction hazard how it can be mitigated. So that means next one is the seismic slope stability analysis. We will discuss about the pseudostatic analysis, pseudodynamic analysis, then seismic design of retaining wall, okay, seismic displacement of the retaining wall, then effect of water in the backfill, how this water position will affect the earth pressure, that will also be discussed. And then as I mentioned, the seismic due to the earthquake, water retaining or the waterfront retaining structure, those are damaged. So how to design this waterfront retaining structure, those will retaining wall, those will also be discussed. Then the static and seismic design of geosynthetic reinforced retaining wall, that will also be discussed. So these are the course plan, and we will go as per this plan. Okay. And then the books or the reference material. So the first one is the Kramer book, Geotechnical Earthquake Engineering. So I will mostly use the first book and some portion in the second book also. That is the BM Das, Fundamental of Soil Dynamics. So mostly I will use these two books. Majority portion I will cover from this Kramer book, and then some portion I will cover from this BM Das Fundamental of Soil Dynamics books also. And then we have a few books, reference books. We have the SwayamPrabha Soil Dynamics, and then Day, so RW Day, so that is the Geotechnical Earthquake Engineering Handbook. So those books also you can collect and see. But in addition to that, I will use several other books also, and when I will use their materials, I will give you the reference of those books, and I will use the number of research publications. Okay, so I will take a few materials from the research publications also, and when I will use those materials from the research publications, then I will give you the reference also of those research publications. Okay, so let's start that. First thing, that one of the first reliable written form of strong earthquake that is available is occurred 780 BC in China. Okay, and in AD 79 in Italy, the eruption of Mount Vesuvius occurred due to earthquake, and which buried the city of Pompeii. Okay, and the largest earthquake ever recorded is 1960 Chile earthquake, which has a magnitude of 9.5. So these are small information before I start our first topic. That, as I mentioned, the first topic I will discuss about the causes of earthquake. So first to discuss what is the causes of earthquake. So there are basically two causes of earthquake. First one is the movement of tectonic plate, and second one is rupture of rocks along the fault. Okay. Now, our earth uppermost part is divided into n number of plates, or number of plates that I will discuss later on. So those plates are called tectonic plates, those plates that float over a more dense fluid-like flowing interior of the earth. So that means the uppermost part of the earth is divided into number of plates, and those plates are moving actually over the dense fluid-like flowing interior of the earth. So because of plate movement, this is one of the major cause of earthquake. Okay, and another cause, as I mentioned, the fault definition, that the faults are localized area of weakness in the surface of crust, in the surface or crust of the earth. That means when the energy is accumulated, this is released along this weak zone. Okay, so that means there is a rupture of this bedrock or the crust and along this fault line and the fault zone, and so there will be the earthquake. Okay, so that means one is the plate movement, another is the rupture of rock along the fault. These are the causes of earthquake. In addition to these two causes, there are some other causes that I will discuss later on. So first we know the first cause, that is the movement of tectonic plate. So we know what are the layers of earth. Okay, we should know what are the layers of earth. The earth is divided into major three layers, that is crust, mantle and core. Now crust, it can be continental crust and oceanic crust. Now thickness of the continental crust is around 25 to 40 kilometer. Average is around 30 kilometer. Okay, and continental crust is 5 kilometer. So that means oceanic crust is 5 kilometer. So that means the continental crust is thicker than the oceanic crust. Okay, then the mantle has two parts, you can see. So this is the mantle, this is crust, which is 5 to 440 kilometers. This mantle has the upper mantle and lower mantle. So upper mantle has a thickness of 650 kilometer and lower mantle is 2235 kilometer. If you add them, it will be around 2885 kilometer. Okay, and the core has also outer core and the inner core. Now remember that outer core is liquid in nature, which has a thickness of 2270 kilometer, and inner core is solid, which has thickness of 1216 kilometer. So this is the rough idea about the different layers of earth. Now discuss in detail about each layer. Okay, so now if I discuss that, the first portion is the crust. Crust is the outermost layer of the earth. Okay, the thickness of the crust beneath the ocean is around 5 to 6 kilometer. So here I have mentioned it is around 5 kilometers. So 5 to 6 kilometer, the thickness of the oceanic crust, which is beneath the ocean. Now thickness of the crust beneath the continent, that varies in the range of 25 to 40 kilometers. Average will be around 30 kilometers. However, under some young mountain range, it may vary from 60 kilometer to 70 kilometer. Okay, so in all you can see the sources of all the materials are given in the slide. So if you want, you can check those sources. Okay, and you will get some more idea about the information that I am giving. Now under large mountain range such as the Alps, the thickness of the crust can be even 100 kilometer also. So that means the continental crust average thickness is around 30 kilometer, but sometimes it can go up to 100 kilometer also for very large mountain range. Okay, so that means the crust is the outermost part of the earth, and this is the cooler than other layers of the earth. So that means this is the coolest among all other layers of the earth. Okay, so crust is rocky or solid and brittle in nature. It can break or fracture due to earthquake. Okay, So now the next part is that the oceanic crust is thinner than the continental crust. So oceanic crust is generally more uniform and denser than the continental crust. The specific gravity of oceanic and continental crust is around 3 and 2.7 respectively, so that the density of this rock or the crust will be, for the oceanic crust it will be around 3 gram per centimeter cube, or unit weight will be 30 kilonewton per meter cube. And for the continental crust it will be 27 kilonewton per meter cube, that is the unit weight of the continental crust. Next part is the mantle. Okay, so mantle is divided into two parts, the upper mantle and the lower mantle. Okay, so you can see that here, that is this is the crust, then the mantle. So it is upper mantle and the lower mantle. The uppermost part of the upper mantle, that means the uppermost part of the upper mantle which is close to the crust, which is also solid or more rigid, and along with the crust they form a layer which is called lithosphere. So that means, what is lithosphere? Lithosphere is the uppermost part of the upper mantle and the crust, and they form a layer that is called lithosphere. So sometimes this lithosphere also called the uppermost part of the earth. Okay, so actually that is the combination of uppermost part of the mantle and the crust. Okay, so and in the definition I have mentioned what is lithosphere. There I mentioned lithosphere. So that means this lithosphere is actually uppermost part of the earth, but which is the combination of crust and the uppermost part of the upper mantle. Okay, and that is basically solid or more dense. Now that is rocky lithosphere, brittle in nature and can break or fracture due to earthquake. Okay, the thickness of the lithosphere under continental crust is more than the thickness under oceanic crust. Here also the thickness of the lithosphere under continental crust is more than the thickness of the lithosphere under oceanic crust. Now what is that thickness? Now under continental crust the maximum thickness of lithosphere can vary in between 200 kilometer to 300 kilometer. So range specifically you can say 40 kilometer to 280 kilometer, because I have mentioned that the crust thickness around your continental crust thickness is around 25 to 40 kilometer, average is 30 kilometer, but sometimes it may go to 100 also. Okay, so that's why here range of lithosphere is 40 kilometer to 280 kilometer, but the maximum range can vary in between 200 to 300 kilometer, which is approximately I have mentioned the 280 kilometer. So here if you see these ranges, sometimes these ranges, these are not uniform, so they vary from site place to place. So that's why I am giving in the form of range. So and that range is 200 to 300, maximum is around 280 kilometers. So that means lithosphere starts from 400 thickness under continental crust will be 440 kilometers to 280 kilometers. That means the minimum is 40 kilometers, maximum can be 280 kilometers or up to 300 also. So now under oceanic crust the maximum thickness of lithosphere is around 100 kilometers, and minimum, that means range is starts from 0 at the ridge to 100 kilometers for oldest ocean floor. So that means this is the maximum I am talking about. 100 kilometers is the maximum thickness. Okay, actual range is 0 to 100. Similarly, under continental crust maximum is 200 to 300. I have given a value of 280. So that means it starts from 40 kilometer, it can end up to 280 kilometer. Okay, so now the lithosphere with average thickness 80 kilometers covers much of the earth. So now if I take one value, because I have given different value For under ocean a range, different range. Under your continental crust, that is a different range. Now if I take want to take one particular value, that is thickness, average thickness of lithosphere, that is covering most of the earth, and that value is around 80 kilometer. Okay, so that is the thickness, average thickness, it's cover much of the earth. Okay, so this lithosphere is broken into 7 major and 14 minor plates. Those are called the tectonic plates. Okay, so that means we are talking about the tectonic plates, because I have mentioned that the major cause of earthquake is the movement of tectonic plates. Now these tectonic plates is what? Actually this lithosphere, which is divided into number of plates. So those plates are called tectonic plates. Okay, that means this lithosphere, which is divided into number of plates. Now here I have mentioned the 7 major plates and 14 minor plates. So now this definition, you will get different numbers in different places. So here because that depends how you are defining their size. So here major plates indicates the plates whose area is more than 20 million square kilometer. That means if the area is 20 million square kilometer, those plates are called as major plates. And minor plates means if the area is in between 1 million to 20 million kilometer square. Okay, so in that way it is been defined, and so it is 7 major plates and 14 minor plates. And the mantle is cooler near the crust, and the temperature increases as depth increases. Okay, so that means the mantle is cooler near the crust and the temperature increases at depth increases. Because of that this part of mantle, as we go below lithosphere, okay, so where the temperature is more than the lithosphere, so as that part, the mantle is in viscous state and semi-molten state, which is called the asthenosphere. So that means the layer below the lithosphere is called the asthenosphere, which is in semi-molten state, because here the temperature is more than the lithosphere. Okay, because of that the material nature is viscous and it is in semi-molten state. Clear? So before I go to the next part, so I have discussed the 7 major tectonic plates. So these 7 major tectonic plates are African plate, Antarctic plate, Eurasia plate, Indo-Australian plate. So that can be divided into Australian plate and Indian plate. Then North American plate, Pacific plate, and South American plate. Now if you look at this picture, you can see here this is your African plate. Okay, so this plate boundary, you can see this is the African plate. Okay, then the Antarctic plate, this is the Antarctic plate. Okay, this is the Antarctic plate. And then the Eurasia plate, this is the Eurasia plate. You can see this part also. Then the Indo-Australia, so some part is here, some part is here. Okay, so this is Indo-Australia plate and this is Indian plate. You can see, so this is our plate, this is the Himalayan region, so this is the Indian plate. Okay, and then the North American plate is, this one is your North American plate. This is the North American plate. Okay, and this is South American plate. And another one is the Pacific plate. So this one is the Pacific plate. So in addition to that, there are a number of minor plates. You can see few of them are shown in this picture. That is, this is your Arabian plate, this is your Filipino plate, now this is your Caucasus plate. So in this way also some minor plates are also shown in this figure. So there are 7 major plates and 14 minor plates, and I have already explained how they are defined by their size. Okay, so in this way, so I am finishing today's lecture. So next class I will discuss further about the mental and other layers of the your earth, and then I will discuss about the more causes of the earth and how to locate epicenter of an earthquake. So all this we will discuss in the next class. Thank you.